composite beams. We've sort of looked at beams while studying composite slabs, but this topic is going to exclusively cover what are the basics of the composite beams, what are different types of composite beams that you can use. Particularly, we have beams that are downstand and shallow flow beams. So this is how a typical downstand beam looks like. So the steel deck is supported on on the downstand beam, and they are connected by what are called as shear studs. These bolt-like members that you see are called as shear studs. These shear studs are welded to the top flange of the beam, and they and that's how there's a transfer of force between the deck slab and the beam. Now, if we go back to Theory of Structures 5 and Design of Steel Beams, there was a phenomenon that the beam was susceptible to, which is called as lateral torsional buckling. So what we said there is, in case there's no lateral restraint to the beam, what might happen is uh, the top flange is under compression, the bottom flange is under tension, and we have seen this in steel is that it has sort of a tendency to buckle. So the top flange, which is under compression, sort of tries to buckle, but the bottom flange is in tension and does not let it buckle. Then the compression flange uh, deflects, and then there's a moment and torsion at the same time. So in order to avoid this phenomenon, in order to avoid the phenomenon of lateral torsional buckling, it is quintessential that these steel decks sort of provide a lateral restraint to the downstand beam. Now, this arrangement is suitable for spans up to 6 to 12 meters. So these are just some descriptive pictures of the arrangement. So this is the Oriental type of steel decking. This is the trapezoidal type of steel decking. This is an actual photo from site. You can see these bolt-like elements that you see. These are the shear studs. Uh, in the absence of the steel decking, you see that these elements are used to provide lateral restraint to the beams. Now, what if you want to span longer? Perhaps you might have to move from, say here you're using rolled steel sections, but now you have to span longer. Say you have to span about 10 to 16 meters. Then the standard rolled steel sections that are available in the market might not be adequate. You might have to go for what are called as plate girders, which are or built-up sections. But if you use a plain, homogeneous built-up section, you might end up providing a very heavy section, and that sort of will increase the weight of the structure as a whole. So there's an option to provide what are called as web openings in this section. So what you principally do is you provide web openings at a location wherein the shear is not a concern. Because, see, we have seen in the past, the function of the web or a majority of the shear is resisted by the web, and majority of the bending is resisted by the flanges. So, if we are thinking about reducing the area of the web, the best place to target is somewhere near the center where shear is not critical. Now, see, you sort of immediately have to imagine the bending moment diagram of, say, a simply supported beam at least, wherein the bending moment is maximum at the center, the shear is zero at the center, and the shear is maximum at the supports. So you see here on the image on the right, there's this web opening that is created towards the center, and you see that these are the stiffeners that are provided so that there's no stress concentration because of this sudden opening. And there is no opening towards the support. That's because shear is larger near the supports. Now, an important function that these openings have is they let the services pass through them, because of which you do not need an extra space for the services. The structural system and the service system sort of occupy the same zone, thereby reducing the effective flow to flow height of the build. So basically, so these are multifunctional. First is that you can span longer, say with 1 meter, 1.2 meters. You can span up to 10 to 12 to 14 meters. And at the same time, you can always provide these web openings and allow your services to pass through. Now, what if your spans are further larger, say about 16 to 20 meters? In that case, there's an option of providing tapered girders. Now, what tapered girders principally mean? So, if this is your beam, simply supported, having UDL, this is the bending moment diagram. So, your bending moment is maximum towards the center, and it is the values are lesser as you go towards the support. So, we can always provide a section like this, a section that tapers towards the center, perhaps some constant depth at the center, and then it tapers back towards the support. Now, what happens because of this is, firstly, again, there's this service integration that can happen, wherein all your services can pass from this space. And another thing is you can also sort of combine the concept that we learned before and this one. So you can also provide web openings in this in case your services happen to pass from the center of the span. And then you can pass services through this. So there are multiple options possible here with the use of uh, a modified downstand beam in the form of tapered girders. Now, if your spans are further longer, which I believe is the case in most of your projects, there are always the spans are always very ambitious, more than 20 meters and so on. There are different options like stub girders, honest composite beams, composite trusses, and so on. So we're not going to get into the details of this as such, but this is just for your information in case tomorrow you really have a really long span and you want to refer to this and sort of research it further as to how you can provide it. And the last type of beams is what is called as a shallow floor. Now, if there's a very strict restriction on the height of the floor, we can sort of integrate the beam and the deck slab. You can see how it is done in this picture. So the section that is used is a asymmetric steel beam. So the flange, okay, don't bother about this opening here because this is just to conceptually show how the rebar flows. It is an actual I section. It's not different 2T sections. It's an actual I section. So it's an asymmetric steel beam with a wider bottom flange than the top flange. We need a wider bottom flange because previously the slab was sitting on the top flange. The metal deck was sitting on the top flange, but here it's not the case. Here it sits on the bottom flange because we have to integrate this space. It sits on the bottom flange. There has to be an at least 50 mm bearing on each side. And now, since there's this reinforced concrete and the rebar is going to pass through, so we need these openings in this beam through which the rebar can pass. Now, doing this optimizes the height of the building and results in a flat soffit, enabling easy passage of services. So you can imagine it's not like the conventional system that we have when there's a slab and then uh, uh, there's again a hurdle because of the beam, and we have beams in a line, and therefore it's very difficult to pass the services. But here there's a flat soffit, so the service is really not a concern. Now, these are ideal for spans from about 4 to 9 meters. Difficulties involved regarding the drilling these holes, passing these rebars. It is not very commonly used, so perhaps you can look at it as a last resort in case your height restrictions are very strict. So I believe this is all you need to know about uh, composite construction, reinforced concrete, steel concrete composite. So any questions as of now? You guys can hear me, right?
Yeah, we can hear
Yes.
you.
Yeah. So the last topic of the season, precast concrete. Have any of you guys used precast concrete in your projects? I think someone has, and someone also had a question regarding the joineries and so on.
Yes, I have to.
Okay, so how has been your experience with it? Has it, particularly when it comes to the information that is available, and difficulty in detailing and so on. So how has been your experience?
I think it's been very, it's also basically for the 2D precast, I think there's a lot of information available, but when you look at the 3D part of it, it's not. So I think that is the whole problem that I was facing because I'm using the 3D precast, and also the joineries, they're not very typical. So I was like told by my guide that it's something that is like very inventive. So it would differ from project to project. So at least for the 3D precast, the joineries become very particular to the project and the design, the way you're designing it. So yeah, that's the whole idea.
So what do you mean when you say 3D precast?
So in that, basically, instead of having so in 2D, how you have every element which is made and it's brought to set and assembled there, but in 3D precast you give the size of a module, like you give the dimensions and everything, and then the whole box itself is made. It's precasted and then it's brought to site and then just attached with each other. So if I have a room, the whole room is made. I don't have to separately bring the beams, columns, and the slabs. The whole room is made in form of a box, and then they are just joined together.
Okay, so instead of elements, you're working with spaces here.
Yeah, so I'm working with like proper 3D cubes and cuboids, and then all of them come on site and they sit together. So the joinery basically I'm using is the tongue and groove joinery, but it's also like when I was discussing it, I think we also thought that it would be better if I give some sort of extra support. So then I had to also settle down for some screwing of them together, or maybe having like a cleat which can at least make it sturdy and it make it like sit on the ground. So that was the whole thing. And again, there are restrictions to it because when I was reading it on the internet, they said that you can't go more than G+2 or something. So yeah, so that's the whole idea.
Okay. Are there any are there any practical examples already?
Yeah, there are examples. Like there are companies in Australia who do it, and there have been a few projects, but most of them are like residential. They are not very highly architectural, commercial example I've come across. So yeah, I mean it's basically for easy construction. So they use it for residential where they really want to quickly just make houses and get it assembled quickly.
Okay, okay. Thank you. So it's good that you are sort of, uh, swimming into uncharted waters and, taking up things that are not very common. And this is what precast concrete needs right now. It really needs people to come forward and, experiment with it, uh, so that it becomes a more commonly adopted practice over time. Anyways, so what happens in a normal concrete construction is that the concrete is cast. It is so the concrete can be, uh, firstly the concrete is made, so it can be made either in the site or at a ready mix plant. It is transported to the site, and then it is placed in different forms as per the site requirement, and it is cured at the site itself. But precast concrete construction is, or a precast concrete is a construction product produced by casting concrete in a reusable mold with wire mesh or rebar, which is cured in a controlled environment, transferred it to the construction site, and left it in the place. So we are casting it, we are curing it in a controlled environment, in a factory or in a plant, and then we are just transporting it to the construction site and lifting it into place. Now, of course, this offers a wide range of advantages over cast in situ concrete. The first and the most important being quality control. Anything that is being produced under a controlled environment of a plant, uh, surely is meant to have greater control over its quality and workmanship. Another important thing is that it sort of uh, leads to proper curing and monitoring. Curing it can be very challenging in different environments, especially if the environment is really hot. Then it there has to be the curing has to be intensive. It has to be done very carefully and so on. So it basically depends upon the climate. But in case you're doing it in the plant, then the external factors do not really play a major role, and you can actually do a very proper curing. And this also eliminates the influence of outside variables like weather. For example, it's always it's difficult to uh, cast concrete in rainy seasons, and particularly in cities like Mumbai, when it rains 3 to 4 months, the speed of construction projects really slows down, and everybody is in a rush in April and May to finish up the their concreting before the rain starts. So there's a lot of reliability on outside variables. So if your products are, if your concrete products are produced in a factory and then this is transported, then basically there's no role that outside elements play in this. Now, practically, you can use the forms that are used in a plant hundreds and thousands of times before they're actually replaced. So what this functionally does, it reduces the cost per unit of the formwork. Then, of course, there's greater safety because precast concrete practically can be produced at the ground level. So it completely eliminates the need for casting concrete at higher levels. So there's a greater safety involved. Uh, Another point is versatility. There are numerous types of precast concrete forming systems. Just what she said, like I've heard of this 3D system for the first time. So as we go on, it's getting more and more versatile. There are more and more options in terms of size, function, and cost, and so on. Then yes, we talked about the efficiency, wherein we said that if it's an in situ construction, there's always reliability on the weather. But here it's not the case. The production can take place throughout the year without dependency on weather. So it's a very efficient process. Then it's consistently durable. Now, one of the major challenges that we face in on-site construction is the uniformity of the depth of cover. Talking about say a beam, somewhere the clear cover is 25, somewhere it's 30, somewhere it's 20, somewhere it's 40. The rebar is going up and down, up and down, up and down. So that sort of results in a differential durability of a single member itself. So there's no consistency in the amount of cover that we have provided. There's no consistency in the effective depth that the section has. And particularly if the cover is very large, where the bending moment is maximum, that actually can be a nightmare because you are effectively reducing the effective depth, and that is something that is not desirable. So maintaining a consistent cover is really important, and this is possible. This is definitely possible when you are doing it in the plant. So that not only increases the durability of the member, but it also enhances um, or I would say the strength of the member is more or less uniform. Then, of course, there's rapid erection on site. There is no waiting period here. You don't have to cast concrete and wait for 7 days, 14 days, 28 days, and so on. It's just like Lego blocks. You just bring it, place it, and so on. There's no waiting period here. And moreover, you can just use it no sooner it is connected. In concrete, so concrete slabs, you have to wait for 14 days. You have to wait for sometimes 28 days till it achieves its strength, and only then you can use it. But here it's not the case; it's plug and play. Then it's perfect for underground applications. Why? The answer is that the precision with which uh, precast products can be manufactured sort of enables an airtight and a watertight joint. Because of this, and I believe that is quintessential in underground applications. You cannot afford air or uh, water or any other substances to pass through. So having a watertight and airtight joint is really important, and that is what is possible if you're manufacturing it in a plant. So all the cable, all the all those concrete cylinders that you can see lying by the road, uh, they may be for a passage of wastewater, or they may be for passage of cables or so on. But all of them are uh, more or less all of them are precast. Then sustainable. So concrete itself is a sustainable material. It uses abundantly the whatever materials that are naturally available, and they can be recycled. When I say recycled, like a lot of researchers are working on how we can, use concrete after it is being demolished. So, in a sense, that we cannot, as of today, we cannot 100% recycle concrete, but yes, research is going on, and to some extent, concrete can be again used as coarse aggregate and fine aggregate in new concrete. Then the byproducts from other industries can be used. Again, there's a lot of research that is going on as to how we can replace some amount of cement with other materials like blast furnace slag, uh, then slags, then sands for different industries and so on. So that serves a dual purpose. That firstly, that reduces a lot of waste, and secondly, that can be, the cost of concrete goes down because the amount of cement that is used goes down. Then it can be reused and recycled. That is something we've discussed. Now, the most important advantage that we get here is easy repairs and extensions. This is something that we had in steel only. In concrete, using in situ concrete, this was not possible because all the joints are monolithic. All the beams, columns, slabs, footings, they're all monolithic. And therefore, it is never possible to repair or replace or extend anything easily. But with the use of precast concrete, it's life is easier. You can always replace elements whenever they get damaged or they are no longer useful. You can also replace. You can also remove an element and use it somewhere else. So that is an important advantage that we get using precast concrete. Now let us look at the common applications. Principally, wherever there is repetitive construction and you don't really much care about how it's going to look like, I think precast is a go-to option. For example, a parking structure. The requirements are simple. It has to be durable. There is a lot of repetitiveness. It has to be economical. And therefore, all this makes the use of precast concrete as an ideal choice. Now, already in parking structure, there are various elements like crash barriers, stairs, paving slab, etc., that already employ precast concrete products. But we can sort of convert the entire system into precast. Then another example is something that you might have commonly seen while traveling in and around Mumbai. That is bridges. Almost all the metro bridges that are being built, all of the slabs, all of the girders, all of the decks that are being used are precast. You can see all those massive members that are transported on the trucks and lifted on site. Then another example is retaining walls. Today we have a wide range of engineered earth retaining systems that include commercial, residential, sea walls. So all the stones. I'm not all the crash barriers. What they are called, wave barriers. What do you call those stones that are placed near the ceiling, near the sea faces?
Tetrapods.
Yeah, tetrapods. They are all uh, precast concrete, and the retaining walls could also be precast concrete. Then we have talked about utility structures like water, wastewater containment vessels, and so on. Housing, a very a very important application of this, and this is what our friend has worked on. That is housing using precast, 3D precast concrete elements. So it's a viable option in countries with rapidly increasing housing demands, ideal for mass housing, and I believe already to some extent in projects like slum rehabilitation and so on, they've already employed precast construction. Now, a study says that it can reduce construction costs by 10 to 15%. It reduces labor requirement because there's a lot of work that is reduced on site. You don't have to erect the formwork, place out reinforcement, cast concrete, and so on. So there's a lot of reduction in the amount of work, and naturally there's a reduced labor requirements. So, but in housing, the structural framing in the majority of the current buildings is load bearing. So we have n number of options when it comes to reinforced concrete. There are hazard type of structural systems that you can use depending upon the height of the building, depending upon the intensity of earthquake or the winds that the building is to be designed for. But here, As of now, the structural framing is in a majority of current buildings is load bearing. So all these walls takes the loads downwards. So let us sort of look at some examples in and around us. So there's this project in B1D, which is G+3, about 250 homes. All the walls are load bearing, and the slabs are also precast. And this design has been designed and approved by IIT Delhi. Then we spoke about slum rehabilitation, one of the projects in Boyewada. This is G+23. So I think that's quite a lot of height for precast. So perhaps this is an example that maybe before there was a limitation as to how high we could go with precast. And even now in the project that she's working on, she says that it is G+1 or G+2 using 3D blocks. But using this mix of 2D and 3D. So I think the 3D blocks here are the toilet blocks. I think the rest of it is all 2D. So we can go up to G+23. So again, these are load-bearing precast walls and precast slabs. And this design is approved by VJTI Mumbai. Then in Chennai, there's a project called Lakeside, which has still +4 load-bearing PC walls. The uniqueness of this project is that they have employed what are called as pre-stressed hollow core slabs. So these slabs can span longer, and because of which the requirement of providing closely spaced walls is eliminated. So this is something that is different from other projects. Then another mid-rise building, which is basement plus ground plus 13 blocks, commune in Bangalore. So the reason for including this is, if you look at the final picture, okay, this might not be the final picture, but perhaps a perspective, drawing. But you do not really understand if this building is precast. So it is a general notion that you can always differentiate a precast building from a cast in situ building. But if you look at this building, I think it's really not the case, and you cannot really say this building is being constructed from precast elements. Then another example that I've included here is the hostel building in SRM 33. The reason for including this is, a lot of times we talk about transfer systems, wherein there is a set of columns coming from the top, but at the bottom you want something like auditoriums, you want a dining room, a banquet hall, and so on. And in that case, unfortunately, the columns have to be transferred to some beams. Now, perhaps you cannot think of it when we are dealing with precast concrete members, but this has been implemented in this particular building, wherein at the ground floor they needed a dining room, and therefore there's a precast portal frame that sort of transfers all the walls and transfers all the loads from the walls to the beams and columns. So uh, a transfer system is also possible using a precast concrete system. Of course, this comes with a set of challenges. Firstly, there's a lack of awareness, acceptability, and availability. An architect or a structural engineer will go for a system if he knows about this system. Okay, now, so definitely there has to be a need to awareness. Now, we don't have courses on precast products per se, but this is something that we as architects and engineers have to look into as to how we can provide better solutions with the use of precast concrete elements. Acceptability is a big criteria. So it's always easier to just keep doing what we know and what has worked for years, and there's always a lot of inertia for change. So for example, there was a small project that we were working on, and there's a different type of slab detailing that we follow, and we sort of gave the slab detailing to the site. And although that was more optimal, that was easier to understand, that was that was a better way of doing it, but there was a lot of resistance because there's a certain way they have been doing it for years, and it is sort of out of their comfort zone to detail in a different way. So ultimately, we had to sort of find out a middle solution, and then we had to budget. So even for such small, changes, there's a lot of inertia. So shifting from in situ concrete to precast concrete is a long journey, and it is going to take time, and there's a lot of resistance to change. Yes, in line with the lack of awareness is also limited experience with planning, analysis, and design of precast buildings. Not a lot of architects and not a lot of engineers have worked with precast buildings in the past. Another major challenge from a structural point of view is there's uncertainty about the seismic performance of precast buildings. Now, in the Bhuj earthquake, some of the buildings were precast, and there was an extensive study that was conducted on the seismic performance of these buildings. The manufacturers or the people who are involved in producing these buildings claim that these are perfectly, yeah, suitable for any for a scale of earth for a good scale of earthquake. But the research perhaps is not from the research. We do not have a clear conclusion as to do these buildings really perform in earthquakes. Then obviously there's a lot of need for standardization and R&D. For example, in steel we have hundreds of sections that we can choose from, but from here there's really a need for a lot of standardization. We more and more companies to get involved to come up with. We do not have a standard per se. There's an IS code for concrete, for steel, but as of now we do not have a code of practice for uh, precast concrete. Perhaps I myself am not aware of any code that the IS gives for precast concrete. So but the point here is the standardization. For example, in steel, the standardization comes from the industry. The Not a lot of sections that the code gives are followed by the industry. The industry is driven by what is the demand. So there's in terms of standardization, it's the industry that sort of spearheads the standardization. So here it is the industry that has to come forward and standardize and research and develop uh, precast concrete. Then there's another question of government taxation policies. Now, cast in situ concrete sort of does not attract any tax because it is not a finished product. It is, yes, cement might, aggregates might, and cement might, but concrete as such does not attract taxes because it is not a finished product. But if you're using a precast concrete product, so now it's a finished product, and naturally it is going to come with a tax. So we also have to look at the tax implications. If tomorrow you decide to undertake a project that is in precast, there's always this perception about precast building being inflexible and having an identifiable appearance. As I said before, that it is almost always possible to differentiate a precast building from a cast in situ building. Then because of the standard sections and so on, it is always difficult to accommodate complex plans and layouts. Now I look at your projects and they are beautiful, but they are really complex. And for such complex projects, it might not always be possible to go for precast. Uh, and it is a general tendency to go for all precast or no precast approach. But it is always possible to take baby steps. Make majority of your building cast in situ, but use some elements that are precast. So you can use this approach when you actually start practicing. Is the call on day one should not be 100% cast in situ, 100% precast. Perhaps you can majority of your building can be precast, can be cast in situ, and some portion of the building can be precast. And as you go on, perhaps you might want to increase the precast elements, the precast elements, and so on. Another important factor is mobility constraints. Now you can imagine all those all those members for the metro bridges. They're humongous, and they have to be carried on very large trucks. But since they are along the highway, it's not a problem here. But in a lot of places, transportation can be a major issue. So what is the use of it if we cannot really transport that member and lift into the site? So mobility is an important criteria. Then labor skill and machinery and installation of precast elements required. Yeah. So although there's a lot of work reduced on site, although you don't have to really place the formwork, cast concrete, place reinforcement, and so on. But you really need skilled labor to sort of make the connections, to make the joinery, and that is really important. So I think this is all you need to know about precast elements, and we can. It is safe to say that we have winded up our syllabus, and we have covered almost everything that the university says we should cover. So any questions with this as of now?
I was just